Good morning. So today I'm going to start on section 6.6, which is quantum numbers. Okay. So section 6.6 has to deal with this, do with these idea of what we call orbitals. So let's talk a little bit about orbitals. Orbitals come out of the mathematics of waves. When we have a wave, we have the potential to have what's called an orbital. So what we said in section 6.4 was that de Broglie came up with this idea that the electron, or any subatomic particle, could behave like a wave. And if it does, it would have wave-like properties like wavelength and frequency and amplitude. And so Schrödinger figured out that, hey, let's try to figure out what the equation for this wave would be for the electron. And that's called the wave function. And the wave function uses the symbol psi. Let me draw that a little bit nicer. Okay, that's the symbol for the wave function. But that wasn't particularly useful for physicists and chemists. So Max Born came up with the idea of probability and intensity. And so what he said was, hey, if we square, take the absolute value and square this wave function, we get something that's proportional to the probability that the electron is in a particular location. So the probability the electron is somewhere. So that's about the best you can do. You can't actually say where it is, but you can at least say where it probably is. And that's called probability. So the results of this, the results of the mathematics, are that you get these three quantities, which we call quantum numbers. And we'll learn about a fourth one later. But for right now, we'll just talk about the first three. Turns out there's multiple quantum numbers in nature. So the first three are n, which is called the principal quantum number. And the value of n is limited. It's a quantized value. It's either 1 or 2 or 3 or 4, all the way up to infinity. So it's counting numbers. Then we have something which is called the angular momentum quantum number, Qn for quantum number. It can take on the value of 0 or 1 or 2, all the way up to n minus 1. Importantly, it cannot be as large or larger than n. N limits what the angular momentum quantum number could be. And then the third one is called the magnetic quantum number. It can take on the values of 0 or plus 1 or minus 1. So it can also have negative values, plus or minus 2, plus or minus 3, all the way up to plus or minus L. So it is limited by L, the values that it can take. And an orbital is a unique set of these three quantum numbers. So when we talk about an orbital, like a 2s orbital or a 4p orbital, that orbital is a set of numbers. So it's, for example, 2, 1, minus 1 would be a particular orbital. It actually has a name. We'll go over the notation for that in a moment. And that would mean that n is equal to 2, L is equal to 1, and m sub L is negative 1, right? Now notice that when L is 1, that's less than n, right? It is less than n, so that's good. And when m sub L is negative 1, that's minus L, so that's okay. Another example would be for 1 plus 1. So notice we put the plus or minus for the m sub L to indicate that it could be positive or negative. So this would be n equals 4, L equals 1, and m sub L equals plus 1. So then the question is, do we have names for these sets? There are names for the sets, and there are shapes that we should see. So let's talk about these orbitals. Okay. They have different shapes. So here's an example of one, this right here. This is what we would call an s orbital. An s orbital is the case where L is equal to 0. So it has this shape here. As n increases, the size of the orbital and the energy of the orbital increases. So this would be perhaps a 1s where n is equal to 1. And this would be maybe a 2s where n is equal to 2. All right. Same shape, just different sizes and different energies. The larger the orbital, the more energy it has. We also have orbitals which are called p orbitals, and this is the case where L is equal to 1. And they look something like this, okay? 2 lobes. Now, this is a little bit exaggerated. I'm putting the atom in the center here, but just merely because that's just all I could find to put this thing together. It's really more accurately, the p orbital would be something like this. The nucleus is tiny, and then the p orbital would look something like that. These are called lobes, L-O-B-E-S, like earlobes, and there are 2 lobes in a p orbital. Okay. The sorry, put this over here. The third type of orbital, so these are just wave functions, is called a d orbital. And like the p orbital, it has lobes, but it has 4 of them, 1, 2, 3, 4, like that. So the wave is vibrating in all 4 of these regions at the same time. And then the fourth one is called an f orbital. This one actually has 6 lobes. So the electron occupies, that's the idea of an orbital, is that the electron is occupying these spaces simultaneously. It's not moving from one to the other. It's just vibrating in such a way that it occupies all 6 of these regions simultaneously. It's a complicated wave, okay? That's called an F. So the orbitals have a notation, and the notation is you put the value of n first, and then you put the value of L second. So you're just putting n and L, and then sometimes there'll be a subscript which kind of indicates what m sub L is. So I'll talk about that in a moment. So here's an example. If n is equal to 2, we would put 2 for n. And if L is equal to 1, we would put a p. And this would be called 2p. So that orbital is called 2p. So that's the notation you're using. So there's a coding system for L. If L is equal to 0, then we call it an S. If it's equal to 1, we call it a P. If it's 2, we call it a D. And if it's 3, we call it an F. If it's 4, we call it a G. If it's a 5, we call it an H. You can go as far as you want. But for the most part, we're only concerned with these first 4. Okay? So really, in a sense, then, what that's telling you is that N is giving us the energy of the orbital, or the size. They're proportional to each other. The larger the orbital, the more energy it has. So they both increase. L is giving us the shape. And then it turns out m sub L is giving us the direction. So for example, for the p orbital, right? P is the case where L is equal to 1. We could have an orbital that's pointing this direction. We could have one that's pointing this direction, or we could have one that's pointing in this direction. So there's actually 3 possibilities, right? So m sub L is what gives us the direction. So for example, this could be m sub L equals 0. This could be m sub L is plus 1. And this could be m sub L is minus 1. It's kind of arbitrary which one is which, because it just depends on your frame of reference, which direction you're looking, right? There is no absolute that this is plus 1 or 0 or minus 1, but we know there's 3 possibilities. For L is equal to 2, m sub L could be negative 2 all the way up to plus 2. So you get 5 directions. So it's kind of weird. You get one like this, one like this, one like this, and then you can get one that's kind of rotated this way, and you get another one that's rotated, and you end up with 5 of them right there. And then the F actually has 7. So this is your F, L equals 3, okay? So memorize this coding system right here. Okay, 0, 1, 2, 3, S, P, D, F. And those S, P, D, Fs are the shapes. We'll do it over it again. S, P, D, F, right? Those are the 4. And then N tells you the energy or the size. So N equals 1, N equals 2, N equals 3 would be bigger, N equals 4 would be bigger, so forth and so on. So the size of these orbitals. So effectively what happens is the more electrons an atom has, the larger the atom gets, because the electrons fill these orbitals, and these orbitals start getting bigger and bigger and bigger. So for example, 1s is smaller than 2s. So if you have an electron in a 2s, it's going to be a bigger atom. Okay. So there's that notation there. So let's take a look at a problem here. Okay, this is the first one. There we go. I'm sorry. Okay. So it says here, complete the table below by filling in the principal quantum number, n, and angular momentum quantum number, L, for each electron subshell listed. Okay. Well, this is really just dealing with the notation that I gave you before, right? So if you have a 4p, which is the first one, in the case of the 4p, n is equal to 4. So that's easy. The principal quantum number n is 4. The p, you have to kind of go through that coding, right? SPDF. You just memorize SPDF 0, 1, 2, 3. So S is 0, P is 1. So that means that the angular momentum quantum number for that 4P would be a 1. So it's 4, 1. Okay. Notice M sub L is not given there, but you could figure out what is possible for M sub L, because M sub L is 0, plus or minus 1, plus or minus 2, all the way to plus or minus L. So for 4P, if L is 1, you'd have 0, plus or minus 1. Right? So that gives you 3 possible values, minus 1, 0, plus 1. Second one, 6D, N is 6. D, SPD, so that's L is equal to 2. Remember, for the L, you start at 0. So that would be 6, 2. M sub L can have different values. It can go from minus L, which is minus 2, all the way up to plus L, which is plus 2. So it could be minus 2, minus 1, 0, plus 1, plus 2. That's 5 different values. It's going to be one of them. Each orbital will have one. So one orbital would be minus 2, another orbital would be minus 1, another orbital would be 0, so forth and so on. So you end up with a lot of possible orbitals, especially as L increases. 1s, that's actually like the most minimal orbital. This is the 1s right here. It's tiny. So the 1s, n is equal to 1, and then L is equal to 0. SPDF, 0, 1, 2, 3. Now, what happens is when you have an L is equal to 0, M sub L can't really take on any more than one value, because it goes from 0 to plus or minus L. But if L is 0, then M sub L has to be 0, and there's only one possible value of M sub L. Okay? That kind of makes sense, because a sphere only has one direction, essentially. 4s, okay, well, n is equal to 4, and then L would be equal to 0, and M sub L would have to be 0 as well, okay? So this question might be a little bit better if they had another column, a fourth column, that said, what are the possible values for M sub L? In that case, for the first one, it would be minus 1, 0, plus 1. For the second one, it would be minus 2, minus 1, 0, plus 1, plus 2. For the third one, it would be 0, and for the fourth one, it would be 0. Okay, let's take a look at another one. Okay, these are all pretty much the same. They didn't really change at all. So I'll go through these real quick. 7s, so n would be 7, and L would be 0. M sub L would also be 0. 6D, n is 6, D is 2, right? SPDF. And then M sub L would be negative 2 all the way up to plus 2, 5 possible values. 5F, n is equal to 5. F would be 3, right? SPDF, so that would be 3. And then M sub L would go from minus 3 to plus 3. That's actually 7 possible values. And then 6P is n equals 6, and L is equal to 1. And M sub L would be anywhere from negative 1 to plus 1. So negative 1, 0, plus 1, that's 3 possible values. Okay, so that's, you know, they call this subshell notation. I'm going to get into that idea of a shell and a subshell now. Let's talk about shells and subshells. Okay, so let's start with shells. So the idea here is that it's useful to think of the atom as having these orbitals, right? So for example, the atom has a nucleus at the center, and then you've got an orbital, which is called a 1s. Okay, so that's an orbital. And then you have another orbital, which is bigger. And in the same atom, it's just going to be bigger, right? It's going to look like this. It's going to swallow up the 2s. I'm sorry, the 1s. So there's your 2s. But then you can also have 2p's. So I'm just going to draw one of them. I really actually went a little too far there. So let me try that again. So there's your 2s. There's your 1s. Actually, maybe I'll use a different color. Okay, so here's the 2p. Actually, you know what? I'm sorry. Let me do this. Let me get this out of here. So let's draw it like this. So there's your 1s, there's your 2s. Okay. So your 2p would be something like this. So there's your 2p. Okay. And then there's actually another 2p that comes over here, and another 2p that comes over here. Right. Remember, each 2p has 2 lobes. And then there's one coming out of the board. I won't draw that one because that'll just make it too messy. So you have all of these orbitals that are surrounding the same nucleus. And it's only really going to be a significant issue when you have atoms with more than one electron. If you have lots of electrons, they're going to go into these orbitals. They're going to occupy these spaces, and they'll start vibrating. You know, they will be vibrating like waves in those particular orbitals. Okay, so here's what we do then. We say any orbital with the same value of n is in the same shell. Okay, and it's useful to number these shells. So what we'll do is we'll call this n equals 1. We'll call this the first shell. Okay, there's actually a notation of KLMN. You don't need to worry about that for this. Okay, and this would include the 1s orbital because it's the only orbital where n is equal to 1. Then you get the second shell. This would include 2s and 2p. Okay, and then you get the third shell. 3s, 3p, 3d. So any orbital where n is equal to 3 is in the third shell. Any orbital where n is equal to 2 is in the second shell. And you can just keep going as far as you want. There's a practical limit to this, which is just how stable the atoms are. See what happens every time you go up a shell level? Every time you go up to the next shell, another type of orbital becomes possible. Now, why is that? Like, why aren't there 1p's or 2d's or 3f's? It's limited by the quantum numbers, because what happens is L is what tells you SPDF, right? That's what tells you what type of orbital, what shape it is. 0, 1, 2, 3. But L is limited by n minus 1. It can never be as large as n. So what happens is, if you take the first shell, for example, n equals 1, the highest value that L can be is n minus 1, which is 0. So you can only have an s orbital for the case where n is equal to 1. Let's take one of the, I'll take the one at the bottom, fourth shell, n equals 4. Well, if n equals 4, L could be 0, 1, 2, all the way up to, 4 minus 1, which would be 3. And 3 corresponds to an f orbital, right? So that's why there's not, a a 1p or a 1d or a 3f, they're subject to these rules of these quantum numbers. That was the big breakthrough. Okay. And again, you can go further. You could go up to a 5th shell and have G, and you could go up to a 6th shell and shell and have 7, and so forth and so on. But these are the practical ones. These are the ones we need to worry about. Okay. So those are called subshells. Okay. I'm sorry, shells. But then we also have what are called subshells. And so these are any orbital with the same value of n and L and L. You have to have both of them be the same, okay? So for example, 2s and 2p, those are not the same subshells. They're the same shell because n is equal to 2, but they're different subshells because in this case, L is equal to 0. In this case, L is equal to 1. So those are different subshells. But any orbital that is here is going to be the same subshell. So for example, if I have 2p, I'll use a subscript here, x, 2p y, 2p z. Any orbital that has n equals 2 and L equals 1 is in the same subshell. So these particular orbitals would be in the same subshell. Okay. All right, so let's take a look at another problem then. What is the smallest possible value of the principal quantum number n for a p electron? Okay, so let's think about that. A p electron, now we're talking about electrons, not orbitals, right? So there's an aspect of this that's important. Essentially what we're claiming is that the orbital is the space around the nucleus, okay? But what we're claiming is that, what we're claiming is that the electrons are in the orbitals. They occupy that space, okay? So often people will use the term electron and orbital interchangeably. They're not exactly the same thing. The orbital is the space around the nucleus, but the electrons occupy that space. So in a sense, the electron, you know, is the orbital, or at least the orbital is the electron, okay? So you'll see those terms used. So what's the smallest possible value of the principal quantum number? So principal quantum value is n for a p electron. Well, p electron is L equals 1. So what's the smallest that n could be if L is equal to 1? Well, if n were 1, then n minus 1 would be 0, and you could only have an s orbital. Can't have a p orbital. But if n is 2, 2 minus 1 is 1, L could be 1, and that would be a p orbital. So it looks like it's a 2. So the smallest that n could be is 2, such that you have a p orbital. Okay, let's try another one. An electron in an atom is known to be in a state with magnetic quantum number m sub L is 0. Okay, so m sub L is 0. What's the smallest value of n that can give you m sub L is 0? Okay, well, if m sub L is 0, okay, m sub L always has that possibility. It's 0 plus or minus 1 plus or minus 2 plus or minus 3. So if m sub L is 0, n could be essentially everything, right? Because L could be 0, but L could be 1, L could be 2. So really it's any possible. So what they want to know is the smallest possible value. That would be 1. The smallest possible value of n is 1. So anything's possible there. It's kind of a weird question. An electron in an atom is known to be in a state with, okay, now we have magnetic quantum numbers minus 2. What's the smallest value of n? Okay, so this is what you do. If m sub L is minus 2, then that means L has to be at least 2, right? L could be 2, 3, 4, so it's got to be at least 2. So the minimum that L could be is a 2, right? Because M sub L goes from minus L to plus L. So if M sub L is minus 2, L could be 2. If L is 2, that means that N's got to be at least 3, right? Because L is limited by N minus 1. So if it's a 2, N's got to be at least 1 greater, which would be 3. So that would mean the smallest possible value of N could be 3. It could be more, but it's got to be at least 3. Okay. Oops. Okay, let's take a look at this one. Calculating the capacity of electron subshells. So again, the subshell, the notation for that would be like 1s, 2s, 2p, right? What's the capacity? So they give you the subshells and they ask you for N, that's easy, right? And the value of L is easy. So the first 2 columns, that's no different than the one we just did. So for the first one, 5D would be N equals 5 and L is equal to 2. For the second one, N is equal to 4 and L is equal to 3. For the third one, N is equal to 2 and L is equal to 1, okay? Now, here's the issue. What's the maximum number of electrons? So let me talk a little bit about that, about finding the maximum number of electrons, okay? So the way I'm going to deal with this is I'm going to do the number of orbitals first, okay, for subshells. And then we'll do electrons. Okay. So here's the issue. Let's take 5D like we just did. 5D, N equals 5, L equals 2. Very good. But now if L is equal to 2, M sub L is minus 2 all the way up to plus 2, right? That's how M sub L works. So how do you figure out how many orbitals there are? Well, as I said earlier, an orbital requires 3 numbers. So you could have this combination, 5, 2, minus 2. That would be an orbital. But you could also have this combination, 5, 2, minus 1. That would be a separate orbital. 5, 2, 0. That would be a third orbital. 5, 2, plus 1. See what I'm doing? I'm just going through this sequence here. I'm just changing that by 1. But these are all going to be the same in the same subshell because they all have the same value of N and L. Remember, a subshell has the same value of N, same value of L. It doesn't say anything about M sub L. It just is N and L. So you can have 5 possible orbitals. These are all in the same subshell. Now, obviously, they're in the same shell too, right? If you're in the same subshell, you got to be in the same shell. But they're not the same orbitals. They are different orbitals, okay? So what that tells us is that for this subshell, you can have 5 orbitals in this subshell, okay? I'm going to talk a little bit more about that in a moment. But now, here's what we can do. How many electrons? The maximum number of electrons in the subshell. That's the 4th column. That requires a 4th quantum number. And that 4th quantum number is called spin. It's actually magnetic spin. The magnetic spin, I'll put this in parentheses as a shorthand. It's called the magnetic spin quantum number. The symbol for it is an M lowercase sub s. And there are only 2 possible values for the electron, plus or minus a half. Okay. Now the half is kind of weird. So every subatomic particle has a spin of some sort. It could be 0, it could be 1, it could be +1. Can it be negative? I don't know if they're negative spins. I guess there are, if it could be -1/2, there could be -1, I suspect. Photons are 1, they have a spin of 1. The electron has a spin of either a half or a negative half, okay? It is not, you know, it's useful to think of it kind of like this, kind of thinking of the electron as spinning. And it can spin one direction or the other, opposite directions. So if it's spinning in one direction, it's +1/2. If it's spinning in the opposite direction, it's -1/2. Okay. And so what we do is we say this: if m sub s is equal to a +1/2, we call it a spin up electron. If m sub s is -1/2, we call it a spin down electron. And there's a notation for this. If it's spin up, we use an arrow pointing up or a half arrow. You could do it like that. That's perfectly fine. If it's -1/2, we use an arrow pointing downward or a half arrow like that. Okay? And here's an interesting phenomenon. It turns out that electrons are capable of occupying the same orbital if they have opposite spins. So electrons can form pairs if they have opposite spin. Again, spin is a shorthand term for opposite values of the magnetic spin quantum number. In other words, one is +1/2, the other one's -1/2. If they do, we represent that paired set of electrons like this. So you can do it that way, or you can do it this way. Okay? And it is understood that the one on the left, the one that's pointing up, is called a spin up electron. M sub s is a +1/2. And the one on the right is spin down. M sub s is -1/2. Opposite spins. Electrons can occupy the same orbital if they have opposite spins. Because there are only 2 possible values of M sub s, that puts a maximum in terms of the number of electrons that can fit into an orbital. A third electron would have to take on a value of +1/2 or -1/2, and it would have the same spin as one of the other electrons. That is not possible. So therefore, only 2 electrons, a maximum of 2 electrons. Be very careful about the terminology. You can have an orbital with no electrons in it. You can have an orbital with 1 electron in it, or you can have an orbital with 2 electrons, but you cannot have an orbital with more than 2 electrons. 2 is the maximum number of electrons in an orbital, so the capacity would be 2. So let me do this. Let me create a new one. Let's come back to this 5D subshell, right? This is called a subshell. And our values 5, 2, -2, those are orbitals. So these are the 5 orbitals. Now let's find the maximum number of electrons in a subshell. Well, each orbital can have a maximum of 2 electrons, right? Spin up, spin down. So each of these can have 2. So how many do you get? Pretty simple. It's 5 times 2. So 10 electrons. So the 5D subshell can have a maximum of 10 electrons. Okay. Now let's look at the next one. The next one's a 4F. Okay, so it turns out for 4F, N equals 4, right? L equals 3, right? SPDF, 0, 1, 2, 3. So what can M sub L be? M sub L can be -3. Just start at the L and make it negative, and then count up all the way to plus L. So how many do you have there? It looks like 7, right? So that means you're going to have 7 orbitals. It's that simple. The number of values of M sub L for a given subshell is equal to the number of orbitals, because M and N and L are going to be the same. So you have 4. I'm sorry, I'm going slow because I'm losing track. 4, 3 minus 3, 4, 3 minus 2, 4, 3 minus 1, 4, 3, 0, 4, 3 plus 1, 4, 3 plus 2, 4, 3 plus 3. So there's your 7 possibilities. Again, each one can have a maximum of, so they're never going to say how many electrons are in here. They're going to say how many can be in there. What's the capacity? What's the maximum number? 7 times 2, you get 14 electrons maximum, right? That's your maximum number. You could have less than 14. You could have 13. You could have 12. We'll see that in a later section. But you can have up to 14. Okay? So I'm going to give you the results here of what happens. Oops. So what happens is if you have an s orbital, if you have a subshell with an s, so this is the subshell. And I'll write NS, right? So some value of N, and it's an S subshell. You can only have 1 orbital, so you can only have 2 electrons. Does that make sense? Because if it's an S, L is 0, M sub L is 0, so you can only have 1 orbital. So that means you can have 2 electrons because 2 electrons can fit into 1 orbital. If you have a P, that means you can have 3 orbitals, which means you can have 6 electrons, right? Why 6? Because 3 times 2 is 6. If you have 3 orbitals and each one can have 2, that's going to give you 6. If you have a D, you have 5 orbitals. 5 times 2 is 10. If you have an F, 7 orbitals, 14 electrons. If you have a G, you have 9. That would be 18. Am I right about that? Yeah, it's going up by 4 because every time you add 2 orbitals. If you have an H, you would have 11 orbitals, and that would be 22 electrons. But again, these are the ones that we need to be aware of, not the other ones. Okay? So these are the maximum number of electrons that can fit into a subshell. So really you have 4 things then. You have S, P, D, F. And we're going to see in a little bit that this is important because it's related to the periodic table. So again, these are our shapes, right? These are the shapes of the orbitals. The values of L are 0, 1, 2, 3. And from those, we can figure out how many orbitals we have, 1, 3, 5, 7. I'm just copying down from over here. And our maximum electrons is 2, 6, 10, and 14. Those are the numbers you want to know. Okay. Let's see. Looks like there's one more type of problem in here. Just to wrap up this section. Knowing the subshells of an electron shell. Okay, so some electron shells. Shell equals 2. You have a 2s and you have a 2p. Makes sense, right? Remember, if n is equal to 2, L can be 0 or 1. Can't be 2. L can never be equal to n. It can be only up to n minus 1. So you could have 2s2p. But if you go to shell 1, now it's really limited because now n equals 1, L has got to be 0. You can't have n equals 1 and L equals 1, according to our series rules. So that means you can only have a 1s. 1s is the only possibility, right? L equals 0, so that's an s. But if you get up to shell number 4, now L can be 0, 1, 2, 3, SPDF. So you could have 4s, 4p, 4d, 4f. And so that's why there are 4f orbitals, but there are not 3f orbitals or 2f or 1f. It's the numbers, right? So like numbers have rules, and you know, 2 times 2 is not equal to 5. 2 times 2 is equal to 4. And likewise, in quantum mechanics, it turns out these waves follow certain rules. And one of them is the energy of the wave is determined by n, which can be 1, 2, 3, 4, 5, but not 1.1, not -1. It has a shape. If we want to think of it as being a shape, it's really the angular momentum quantum number, and that's L. L can be 0 or 1 or 2 or 3, but it can't be equal to n or greater than n. It can only be up to n minus 1. And this doesn't have it in there, but there's also a rule about m sub L, the magnetic quantum number. And there's also a rule about m sub s in terms of electrons. Electrons follow these rules that they can either be spin up or spin down. And that will give you further information, like how many orbitals are there for a given subshell, and how many electrons can fit into that subshell, how many can fit into a shell, right? So all of those rules are given by these series of quantum numbers. Okay, and that's the last one from that section. Now, the next issue is section 7, which is kind of going back a little bit in a way. Like I feel like this is actually kind of simple, but let's take a look. They're fun. These ones are easy, but they're fun. So section 6.7 is getting into this issue of how do you recognize different types of orbitals. So this one is S and P orbitals. How do you recognize them? So the questions are there any S orbitals, or is there any, P orbitals? Which ones are they? So there's different shapes here. And all of these are particular types of orbitals. They do exist in nature. Well, actually, I'm not sure about the second one. But the first, the third, and the fourth one, A, C, and D definitely exist. But they aren't necessarily the orbitals we've been talking about. We'll learn more about different types of orbitals later. So what we're dealing with are called atomic orbitals, hydrogen-like atomic orbitals. So look at the first one. The first one has 2 lobes. That should kind of jog your memory, right? The 2 lobes. Now, they are drawn a little bit differently. Different people draw them differently, but that's a p orbital. A is a p orbital right there. Okay, it's got 2 lobes, so that's a p orbital. Second one is a little donut, a little toroid. We haven't seen those yet. So that is not an s orbital. That is not a p orbital. It's not a d or an f either. The third one, that's just a sphere. Well, hey, there you go, sphere. That's an s orbital. So C is an s orbital. And then the last one, D. D has 2 lobes, right? 2 lobes. 2 lobes is a p orbital. So there's your 2 lobes. That's a p orbital, separated by a center. Okay, there's a certain type of symmetry there. So P, S, none of the above, P. Okay, let's look at another one. This is interesting. Look at the first one, A. A has 4 lobes. 4 lobes, that's our d orbital. Second one, B, has 2 lobes. That's a p orbital. Third one is a donut again, a toroid. That's none. And then the last one has, oh, now that's interesting. That's an interesting type of orbital. That one is what we call a hybrid orbital, but it's not an S or a P. It's actually a mixture of an S and a P. So that one's none of the above. So we have 1 d orbital, the first one, which it doesn't ask. It doesn't ask us to recognize D. So you should recognize that as a D, but it's not an S or a P. Second one is a P. So there's no S orbitals here, but there is a p orbital. Okay. Any other interesting shapes? Nothing we haven't seen before, right? So that's pretty obvious. Okay. So that is the first problem. The second problem is, doing relative energies. Now, for this one, I want to get into this idea of energies. Okay. So look at the problem. What they do is they say you've got 4 different types of subshells, 6p, 6s, 5p, and 4f. And they want you to list them in the order of increasing energy. So I'm going to go over that. It does have a little note here that says, I don't know why it says advanced students. You may assume these subshells are all in an atom with many electrons, not just a hydrogen atom. So let me talk about energies now. This is cool because this is where we're going to get into all the cool stuff. Okay. So subshell energies. So first, we're going to deal with hydrogen. And we're not that concerned with hydrogen, except that it's sort of a jumping off point. Okay, hydrogen. So all of these orbitals, n equals 1, 2, 3, 4, L equals 0, 1, 2, 3, M sub L is -1, -2, all these values. These are all calculated values for hydrogen. So we'll start with hydrogen. And here's what happens. It's very simple. This is energy. It turns out the only thing that matters in terms of energy is the value of N for hydrogen. So what I'm doing is I'm drawing little lines. Okay. And actually, I don't like doing it that way. Let me just erase the 2s, the 2p. I'm sorry. I think that's drawn a little bit better there. So notice there are 3 orbitals for the 2p. Why? Because M sub L can be -1, 0, or +1. So there's 3 orbitals there. Okay. Notice the 2p orbitals are at the same level, right? Meaning vertically. This is energy in this direction. So this is increasing energy in this direction. So anything that's at the same, anything that's horizontal is at the same vertical level is going to be the same energy. So all 4 of those orbitals have the same energy. Okay, so that's why they're saying increasing energy. So the only thing that matters for hydrogen is what the value of N is. The 2s and the 2p are the same. And then you have the 3s and the 3p and then the 3d. And there's 5 of these 3ds, right? Because if it's a d, L equals 2. So M sub L could be from -2 to +2. That's 5 different values. Here's your 3p. I won't put the little stretchy lines there. Okay. So all of those subshells are at the same energy for hydrogen. So if this question was, what's the relative energy for hydrogen? All you do is you look at the value of N. The higher the value of the N, the more energy it has. And these energies get closer and closer to each other. 4s. So, 4p. 4d. I'm just scrunching them in here. F, right? So 4s, 4p, 4d, 4f. Actually, it's probably a better way to do this is just write it this way, because now you see the pattern, right? So in increasing energy, it goes like this: 1s, the 2s, 2p are the same, 3s, 3p, 3d, those are the same, 4s, 4p, 4d, those are the same, and you can keep going. 5s, 4p, I'm sorry, 4p, why did I do that? 5s, 5p, 5d, 5f. Okay. Oops. 4f. I forgot the 4f. Okay. Now there's G, right? So you could also do 5G. Okay. And you can keep going as far as you want. Okay. But we're not that interested in hydrogen, to be honest with you. I mean, if we were doing experiments, we would first start with hydrogen and work on it, try to understand it. But later on, we would be interested in other elements. So here's what we're going to do next. We're going to take this energy level diagram and then recalculate it for the case where you have more than one electron, where you have 2 or 4 or 10 or 92 electrons. It turns out that affects these energy level diagram. It changes it. So we're going to call this multi-electron atoms. And that's what we're more interested in. Okay? So the multi-electron atoms works this way. Now, this is increasing energy. So let me start this over. So this is increasing energy. Oh, here, I'll put an E like that. Okay. What happens now is not only does N matter, but now L becomes important. And it's not obvious to figure this out, but here's what happens. In general, as N increases, the energy increases. But now L matters as well. So as L increases, the energy also increases. So now you get what we might call a splitting. The 2p subshell splits off from the 2s and it's higher in energy. And then you have the 3s. Now I'm drawing them approximately equally spaced now because if I draw it the way it really is, they'll get so scrunched together you won't be able to read any of the text. I'll show you in a moment what the kind of more relative energies are. So then 3p is higher. And then 4s. And then 3d. So now it starts getting weird. So now actually the 4s is lower in energy than the 3d. Just turns out to be that way. And then you get the 4p. Okay? Then you get the 5s. And then you get the 4d. And then you get the 5p. And then you get the 6s. And then you get the 4f. And then the 5d. Now you might ask, why am I going up so far? Why so many orbitals? Remember, each of those lines represents an orbital. That's a lot of orbitals. And the reason is, what did we say about electrons? The maximum number of electrons you can fit into an orbital is 2. But we have elements that have hundreds, well, over 100 electrons. Uranium is 92, plutonium is 94. We can get up to 100 electrons. There's actually up to element 118 now, right? 118 electrons. Where are those electrons going to go? They're going to go into these orbitals, but you can only fit 2 into each orbital. So if you can only fit 2 and you have 100 electrons, you're going to need 50 orbitals to put those electrons in. And that's assuming they all have 2. Some of them only have 1. So if that's the case, you're going to need a lot of orbitals. Okay. Now I want to show you kind of a little bit more accurately what the relative distance between these energies are. See how close the 2p is to the 2s relative to the 1s? They really start scrunching up. They get a lot closer to each other. This is called convergence, right? They're converging, they're getting closer. And what it does, they keep converging until you reach a limit, which is essentially infinity. Doesn't matter if it's N, P, D, or F. They all start getting so close to each other that you reach a limit, and that's called convergent. And that limit is called the ionization limit. We'll talk more about ionization later, but essentially it is the case that going from 1s, which is the ground state, right? That's the lowest energy orbital, all the way up to the maximum where n is approaching infinity, right? This is a calculus issue, right? N is approaching infinity. It's not equal to infinity. You can't equal infinity, but you can approach infinity. Then essentially you reach this limit, okay? And that's called the ionization limit, okay? So this is for multi-electron atoms, and that's what we're going to be interested in, okay? So let me go ahead and do the next problem, which is list these electron subshells in the order of increasing energy. Okay, and again, we're assuming these are for atoms with multi-electrons. So there's got to be, essentially, it's not that obvious, right? Because what happens was in multi-electron atoms, these orbitals start getting so close to each other, they start replacing each other, and the order gets more complicated. So, you know, what I've done over the years is I've just memorized it up to a certain level. I can't even say that I've memorized it all the way, but I've memorized most of it. So I can do the ones that are pretty low numbers, like 1, 2, 3, 4, 5, I start having problems. So it's 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. And that's pretty much as far as you got to go, because once you get up to 7p, you're up to element 118 electrons, and there's no further, you don't need to go any further, right? So I've memorized that, but it's taken me many years to do that, and I'm not very good at memorization. So what I would recommend is a table. And so let me show you the table. And then you just use these tables, just use this table when you do it, okay? Here's the order. 1s, 2s, and then see how I'm gonna write this table. This is what I do just to kind of prove to myself that I got the right answer. Again, you don't need to go beyond 7 because 7 is gonna get you up to such a high orbital that. So see what I'm doing? I'm writing a column with the S's going from 1 to 7, and then I'm doing the same thing with the P's. And then I'm going to do the D's. But notice every time that I go to the next type of orbital, SPDF, I start one further up, right? Because you can't have a 2D and you can't have a 1P. So then you do this. And you shouldn't really need to go beyond this. Okay, I think that's as far as you need to go, to be honest with you. Okay, so here's what happens. You start with the little diagonal line with the 1s. So the order, this is going to be the order of filling. You're going to start with the 1s, and I'm going to do it horizontally, okay? Then you do a little vertical line here, 2s. Then you do a little diagonal line. So 2p, 3s. And then once you get through, once you've run out of the s's, you go back and you do the next one. So then 3p, 4s. And you just keep going, okay? So 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, and then you're done, because there are no elements, at least not now. I mean, at some point, you know, maybe they'll come up with some elements at 119, 120, but for right now, that's as far as we need to go. So you're just going to keep going all the way to 7p. And, you know, they're not going to have you do 7p, but they might have you do 5f. They'll have you go up to there. So here's the example. What they did was they gave us these ones, 6p, 6s, 5p, and then 4f. And they wanted to rank it in the order of increasing. So we're going to go this direction. Okay. So let's start with the lowest. The lowest, well, let's go through it. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, nope, 5s, nope, 4d, nope, 5p, there's a 5p, so that's our first one, so it's 5p. So that would be less energy than. Then we have a 6s, there's our 6s right there, so less than 6s. And then we have a 6p. You have to come all the way over here. Oh, 4f. I forgot the 4f. That's right there. So 4f and then 6p. Okay, so that's the order that you're going to have. So this is increasing. Okay, 5p is less than 6s, which is less than 4f, which is less than 6p. Okay, so there you go. That's pretty straightforward. Now, the last topic of this section of this chapter is section 6.8. Okay, so let's talk about 6.8. 6.8 is dealing with electron configurations. Okay, electron configuration. That's essentially what we're dealing with here. And there are several problems in this set, like 5 of them, okay? So here's the issue that we're gonna do. We're gonna do what's called electron filling. And to do that, we're gonna use something called the Aufbau principle. The Aufbau principle essentially just means filling up. We're going to fill up these orbitals. So we fill the orbitals with electrons. Let me underline this. With electrons from low energy to high energy. Okay, so that's why that previous problem where they gave us the ranking of the energy levels, the ranking of these subshells, that's important because this is how we're going to apply the Aufbau principle. Okay, now what happens is, remember, each orbital can only have 2 electrons maximum in an orbital. Now, why is that? That's called the Pauli exclusion principle. Okay. The Pauli exclusion principle says that in an atom, you cannot have 2 electrons with the same 4 quantum numbers. Impossible. Infinite amount of energy would be required to squeeze electrons to the point where they have the same 4 quantum numbers. Now, they can have 3 that are the same, but they have to differ in at least one way. Electrons require that. Photons do not. And so for that reason, you can squeeze photons, essentially infinitely in toward each other and have as many photons in a space as you want. But electrons are limited by the Pauli exclusion principle. It's a statistical law of nature that certain particles cannot be squeezed into the same space with the same 4 quantum numbers. Okay? That's important for us because it turns out that's what creates chemistry. If the Pauli exclusion principle were not true and you could squeeze all the electrons into the same space, then essentially what would happen is there would be no difference between carbon and nitrogen and oxygen and fluorine. They would all behave the same. And if they all behave the same, there wouldn't be planets. There wouldn't be, there'd just be hydrogen, I guess. Everything would act just like hydrogen. Okay. The universe would be very different. So no, electrons in an atom, so if they're in the same atom, must differ in one, at least one, I'm sorry, at least one value of the 4 quantum numbers. So what that does then is it means that you can fit 2 electrons into one orbital. So let's say, for example, this is a 1s orbital. So for each of these electrons, it's 1, 0, 0, but the first one's plus a half. For the second one, it's 1, 0, 0, but it's minus a half, right? So they differ in at least one value, okay? So that's the Pauli exclusion principle. There's one more rule that I'm going to go over, and that's called Hund's rule. Okay, so rule 1, Aufbau, which just says put the electrons in the lowest possible orbital first and then go to increasing energies. Put a maximum of 2 electrons into each orbital. And then the third rule is called Hund's rule. So this is 2, this is 3. So Hund's rule says that in a subshell, place electrons 1 orbital at a time until all are filled. Then place a second electron. Okay, so in a subshell, put 1 into each orbital till you've got 1 in each orbital. Then if you have more electrons, put them in, pair them up, put them spin down to the first. So go like this. Oops, sorry. So for example, like 1, 2, 3, and then once each of those orbitals has 1, 4, 5, 6. And that's the order of filling. It's called Hund's rule. Has to do with magnetic properties. I'm not going to go into it in detail. Okay. So often it's the case that these orbitals are represented, so orbital diagrams, they're often represented either like this, 1s, 2s, 2p. That's an easy way to do it with little lines. But they can also be done like this, a little box, like that, or like that. They can also be done with little circles. And you put the electrons on the inside. All right. So you can, you could do it like this, 1s, 1s, or 1s, okay? So depending on where you look this stuff up, you're going to see different ways. Some people do lines, some people do boxes, some people do circles, okay? Doesn't really matter. It can also be done horizontally or vertically. So if it's done horizontally, you might have like this, 1s, and then 2s, and then 2p. Okay, so that's horizontal. Could also be done vertical. Okay, so you might see, here I'll do it with a circle. 1s, 2s, 2p. So it could, you're going to see it in all kinds of different ways. Okay, just be alert to it could be done in any different way. The electrons are represented as arrows, spin up, spin down, maximum of 2 electrons into each orbital. Okay, Hund's rule is the one that people often forget. When you're ordering it, do 1, 2, 3, 4, 5, 6. Remember, this is a subshell. So you fill this one first, then fill this one, then apply Hund's rule here. 1, 2, 3, 4, 5, 6, and then you're set. So let's take a look at our problem. Draw the electron configuration for a neutral atom of cobalt. Okay, I just want to see the explanation here just so that I can see how they're, oh, I see. So they're doing it with little boxes. Okay, very good. So cobalt. Cobalt is element number 27, so it has 27 electrons. Okay, so the first thing you do is pull out the periodic table, look up the element, look up the number of electrons that that particular element has. That's your first step, okay? Okay. Next thing you do is you pull out your energy level diagram. Remember? This little chart. Okay. And you do 1s. So I'm going to do it this way. I'll use boxes and I'll write that next to it. So 1s, then 2s, then 2p, then 3s. I'll actually connect those because they're at the same energy. Again, these converge, but we're not representing it that way. Oops. Because it, it just gets too messy. Okay, so I'm just going up and up and up. 3p, 4s, 3d. It turns out the 3d is all we need to do here. And you'll see. Okay, so there's your 3d, okay? 1s, 2s, 2p, 3s, 3p, 4s, 3d. 27 electrons. So off-bound principle, you fill up the lowest one first, maximum of 2. Do the next one, maximum of 2. Now you apply Hund's rule. It's a subshell. So you do 1, 1, 1. All spin up. Then once there's 1 into each of them, then you go spin down and pair. Those are called paired electrons. So we're up to 10. You just go all the way up to 27. 1, 2, 3, 4, 5, 6. 1, 2. I'm just counting up to 27. See how I'm using Hund's rule here? Okay, I think that's 27. There's 2 here. 6, 2, 6, 2, 2, 4, 6, 7, right? So 2, 4, 10, 12, 18, 27. That's 27 electrons. Okay, and there you go. There's your electron diagram. Box diagram is what Alex calls it, right? It's called a box diagram. It's an electron filling diagram. There's many different names for these, but it essentially is the electron. This is called the electron configuration. Okay, now this can be written. Instead of using a diagram, we can write it as notation. We would just write 1s2. The superscript is how many electrons are in that subshell. So there's 2 electrons in the 1s subshell. 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Okay? Now I want to make a note here that if you look at the 3D subshell, there are 3 electrons that are unpaired. When you have unpaired electron, the atom is called paramagnetic. It gives it certain magnetic properties. So any atom that has unpaired electrons, it essentially acts like a little magnet, a little weak magnet, and it's called paramagnetic. So cobalt is a paramagnetic element because it has 3 unpaired electrons. All the other ones are paired. Okay, let's try another one. Oops. That was a transition metal. So let me do one that's not a transition metal. I'm going to do helium. Helium only has 2 electrons. Actually, let's do another transition. Well, let me see what we've got here. I'm scrolling through a bunch of them. I want to do one that has a lot of electrons. Oh, wow. Cobalt comes up a lot. Zinc. That's okay. It's a transition metal, but let's do zinc. Okay. Okay, so let's do the box diagram for zinc. Okay, zinc is element number 30, so that means we have 30 electrons. So 1s. I'm just going to kind of, I know these because I've done them so many times. But start thinking about how many electrons you can fit into these, right? You can fit 2 into the S and you can fit 6 in the P. So that kind of gives you an idea of how many boxes you're going to need to do, right? Another way to do it is to think, hey, what did I just do? I just did cobalt. It had 27, right? So if cobalt had 27, zinc has 30, that's only 3 more, right? It's only 3 more. So it's going to look a lot like cobalt. This is 3D, sorry. And then this is 4P. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And you actually look, the 3D is filled. No unpaired electrons. If there are no unpaired electrons, it's called diamagnetic. It actually weakly, if you have a magnetic field, it will actually repel the magnetic field slightly, weakly. So no unpaired electrons is called diamagnetic. Paramagnetic is when you have unpaired electrons, okay? And again, you can write the notation down this way. 1s2, right? 2s2, the superscript is the number of electrons in that subshell. And there you go, 3D. That should add up to 30, right? The superscripts should add up to 30. 2, 4, 10, 12, 18, 20, 30. So there you go. So zinc is number 30. Okay. All right. Now, let's take a look at an issue where we are doing some sort of evaluation. So this is sort of the opposite. They give us the configuration, find the chemical symbol, how many electrons does it have, and how many 2s electrons are in the atom. This is easy, having done what we just did. To find out what element it is, just add up all the superscripts. That'll give you the number of electrons. So 2, 2, 6, 2, 6. That looks like 18 to me. 2, 4, 10, 12, 18. So 18, you look that up on the periodic table, and that would be argon. Argon is element number 18. How many electrons does it have? 18. How many 2s electrons? Only 2. You can only have up to 2 2s, right? The superscript is the number of electrons for that particular subshell. Okay, let's take a look at one more. Neutral atom, this is pretty close. This actually goes up to 3p5, okay? So if you add those superscripts, you're gonna get 17. 17 is chlorine, so the chemical symbol Cl for chlorine, 17 electrons. How many 1s? 2, right? There are 2 electrons in there, 2 electrons in the 1s, okay? So that's pretty straightforward. Oops, sorry. Okay, let's do this. Okay, next one. Okay, electron configuration. I've already kind of done that, sort of gave it all to you at once. What's the electron configuration of carbon? So carbon, you look that up in the periodic table. That's element number 6, so it has 6 electrons. and you just do the configuration just like you did with the box diagram. 1s2, 2s2, 2p2. So we'll go through this one. This one's easy because we already did zinc and we already did cobalt. But carbon has 6 electrons. So we do our little box diagram. Now, the box diagram is the picture, right? That's the little diagram like this that you're drawing that shows the arrows to represent the electrons. So 1, 2, 3, 4, 5, 6. Remember Hund's rule, right? 2 unpaired electrons, so carbon's paramagnetic. But they want the electron configuration. So this is the box diagram. The electron configuration is a little different. The electron configuration is you just take, there it is, 1s2. Remember, the superscript's the number of electrons, 2s2, and then 2p2. Okay, that would be your electron configuration. Okay, that's pretty straightforward as well. And similar type of problem is they're just going to have you do it with more electrons. So writing the electron configuration of a neutral atom with a filled d subshell. Okay. Writing the electron configuration for a neutral atom of xenon. Okay, so xenon is number 54 electrons. Okay. Electron configuration means you don't have to draw the box diagram. You just need to do the configuration. So that saves you a lot of time, right? The diagram is annoying in a sense, but they're kind of cool looking pictures. So xenon, Xe, it's number 54. Okay. So then again, you're going to take that, this thing right here. We're not going to go that far. I mean, 54, does 54 go up into the Fs? Maybe it does go up to the Fs. I don't think so. I think it just goes through 4D. Well, actually, let's see. Let's see how far it goes. 54. So we start with the 1s. Remember, you start here, and then you do these. Just like that, okay? So 1s, I'm just going to write these first, because I know I've got a 2p, 3s, 3p. I know that I've got to go up pretty far up, 54 electrons, right? So 3d, 4p, 4s. Oh, sorry. 4p, 5s. I did that too quickly. So you get the 5s, then you get the 4d. Then you get the 5p. I think this is where it's going to stop, actually, but let's see. S's can go up to 2. P's can go up to 6. D's can go up to 10. So let's see how far we are. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48. We're getting pretty close. P can go up to 6, right? Hey, that's pretty cool. That actually worked out to 54. And there you go. So there's the electron configuration of xenon. Now, I want to show you the pattern here, or a couple patterns, I'm sorry. So what happens is you start filling the S, then the P, then the D, then the F, but you start kind of revolving around. You go 1s and then 2s and then 2p and then 3s and then 3p and then 4, so like you're getting some kind of pattern of how it fills. So here's what happens. In the first column, which is column 1a, let me actually write 1a closer to it. Here's what happens. You get NS1 is the sort of end of it. So hydrogen is 1s1. Lithium is 2s1. Sodium is 3s1. Potassium is 4s1. Rubidium is 5s1. And cesium is 6s1. Francium is 7s1. Sorry, francium. FR for France. Okay. So, you know, there's some patterns in terms of how these work out. Second column here, you have beryllium, magnesium, calcium, strontium, and barium, and radium. So this is 2A. So the outermost electrons end up being NS2, right? So beryllium is 1s2, 2s2. Magnesium is 3s2. Calcium is 4s2. So let me write the row numbers, the family numbers. I'm sorry, the period numbers. Okay, so the outermost for hydrogen is 1s1. The outermost for lithium is 2s1. The outermost for francium is 7s1. The outermost for strontium is 5s2. So these are all s2s. Okay. For that reason, those two columns together are called the s block. Isn't that cool? The s block. So that's a quantum mechanical way of describing parts of the periodic table. Instead of calling them the alkaline metals and the alkaline earth metals, we call them the S block, having to do with their electron configurations. Now, next, you come over to the middle part here, which is our transition metals, right? The transition metals, which are, it's pretty wide here. There's 10 elements there, right? So it starts with scandium. Okay, let me actually bring up a periodic table. Sorry, this takes just a minute. Jeez. Okay, so you got scandium and then titanium and then vanadium and then chromium and then manganese, right? So those are the first 5 elements of the transition metals. Then you get iron, and then you get cobalt, and then you get nickel, and then you get copper, and then you have zinc. So here's what happens here. What you get is this starts at n equals 3 and not 4. So you subtract your n, and then it's D1, D2, D3, D4, D5, D6, D7. There's a couple of exceptions here, but this is the general trend. I'll talk about the exceptions in a moment, okay? So essentially this is called a D block then, right? So those are the outermost electrons, you know, in their electron configurations. And then you get to the nonmetals, right, which is, we're going to call that the P block. So let me start here. Boron, carbon, nitrogen, oxygen, fluorine, and then neon. And we're going to call that the P block. So it's P1, P2, P3, P4, P5, and then P6. And so for this one, you can use the same notation like we did here. So if it's in the second row, it would, for like boron, 2p1. Neon would be 2p6. And then you can just use these numbers here. Now, like I said, there was a couple of exceptions over here. Chromium and copper are a couple of exceptions. So what I'm going to do is I'm going to draw up here. It's just easier for me to bring this up. So what I'm going to do is I'm going to Google a periodic table, and I'm going to do the electron configuration. I almost spelled it right, of the periodic table. There we go. Let's see if this works. Images. There There we go. Periodic table with this. This is what we're doing. We'll see if it works. Okay, so a little, oops. Boy, that's hard to see. Let me do it this way. So hard to see. Okay, there we go. All right, hopefully this is getting a little better. Would have been better to, oops, just have a document. Okay, let me stop share that. I'm sorry, it's just not working very well. Let me bring it up again. I'm just gonna have to close this. Bring that up. Okay, let's try it again. Jeez. Okay, hopefully you can see this. So see what they're doing. I mean, it's really, really small, unfortunately, so it's really hard to see this, but when you Google it yourself, you'll find it. Hydrogen, what they're showing you is a notation of the electron configuration. So they're showing you the hydrogen is 1s1, right? You can see that up at the top. Let me see if I can just go a little bit more. It's really hard to see this. And the internet speed is real slow right now, so it's not real good. Okay, I can't make this any bigger. So hydrogen is 1s1. Lithium, see how it says 2s1? And then next to it is helium in brackets. Helium is 1s2. So lithium is helium 1s2 and then 2s1. So they're showing you the noble gas that comes before that element. They're showing you its configuration just using the symbol of the noble gas with brackets. And then they're showing you the outermost electrons. So beryllium is helium and then 2s2. So it's s1, s2. Then you get to the transition metals. Again, it's really hard for you to see this, but it says 3D1, 3D1, and then 3D2, and then 3D3. And then notice here, it's actually 3D5. So for the chromium, it's an exception, okay? And then the same thing happens for copper. You get an exception. So copper, you would think it would be 3D9. It's actually 3D10. And what happens is one of the outermost electrons from the fourth shell, so 4s, is promoted into the 3Ds. So instead of getting 4s2, 3D9 for copper, you get 4s1, 3D10. And that happens with copper, silver, and gold. So if you pop up on one of those, there's going to be a little exception there. Okay. So and then finally, down at the bottom, so it used to be you could find a periodic table really easy that worked to show this, but now everybody's selling periodic tables. So you get drowned out on Google with things that are trying to sell you this. They're not going to show you a nice one. They're just going to try to sell you one. So the bottom, those bottom two rows are the F block, right? So 4F and 5F. So they're called the lanthanides, in which the outermost electrons are in the 4F. And then the actinides, the outermost electrons are in the 5F. Okay, so 4F, 5F. That's called the F block. Okay. So that's a really brief rundown on the periodic table and the notation that we use there. So work through these problems, and that's pretty much all of the problems for chapter 6. So what I'm going to do tomorrow is I'm going to get a jump start on chapter 8 so that we can start going through that. Chapter 8 is also a very long chapter. It has a lot of sections in it. We're going to do a lot of what are called Lewis structures. So these electron configurations will be important in terms of understanding chemical bonding, and that's what we'll work on tomorrow. Okay, so have a great day. We'll work on 8 tomorrow. Next week, we'll continue with 8. I want to leave a little bit of time next week for chapter 9, which is all extra credit, but I would like to go over it. So we should be able to wrap up chapter 8, maybe by Wednesday, and then we'll start working on 9. And then that's pretty much the end of the course. So take care.